Okay, hey everybody. Welcome back to week 2 of our online learning here. I hope everybody's doing okay. Thank you all for those of you that answered the Google form I sent you, checking in. If you didn't, go back and check your email from Monday morning. There's a Google link in there that I need you, a link to a Google form that I need you to fill out for me. It would be helpful. Alright, so we talked about exponent rules and exponential growth last week. So this week we're talking about exponential decay to start with. And then we're going to talk about exponential regressions. So we'll wrap that up. And we've done regressions with both linear equations and quadratic equations. So it's the same setup as it is for both of those. It's just a slightly different command. So we'll look at that this week. And then next week, we'll move on to our next little mini chunk. All right, so for this one, this graph has been making the rounds, and so I wanted to share it with you guys a little bit. This time looking at exponential graphs as our y-axis, and our x-axis is months, and obviously in March, the looking at exponential graphs has increased because everybody's been looking at the news and seeing all those exponential graphs. So I just thought it was silly and I wanted to share it with you guys. But let's go ahead and jump into exponential decay. Alright, so for this one, when it's exponential growth, we were multiplying by a set number, and it's the same for exponential decay. It's just we're multiplying by a smaller number. It's a number that has to be in between 0 and 1, and what that's going to do is decrease our amount. That's why it's exponential decay. So for example, if we were multiplying by 1/2, that would cut everything in half every time. If we're multiplying by 1/4, cut everything by 1/4 every time, and so on. And so for this one, they're saying, suppose at the end of the school year, you knew 200 Spanish vocabulary words. Unfortunately, each week of summer break, you forget 10% of the words you knew the previous week. Complete the table showing how many words you still know each week for 5 weeks. Alright, so if you're forgetting 10%, that means you're still remembering 90%. So what you want to do is you want to multiply by 90. But we're going to use 0.90 because we have to always write it as a decimal. So if I do 200 times 0.90, that's going to give me 180. So after the first week, I would have forgotten 20 words, and I will remember 180. If I do 180 times 90, that's going to give me 162. I would have forgotten 18 words that week, so I'd only be left with 162. And then this next part, it's where the numbers start getting a little wonky. So when we're working with these, go ahead and round your decimal places to something that seems appropriate, usually 1 decimal place or 2. When we get into the word problems, though, you got to pay attention to the context of the problem. They're asking about population. You can't have half a person at the end, so you would need to round that to a whole number. If they're talking about money, you want to round it to 2 decimal places because money has 2 decimal places. All right, so for here, if I do 162 times 0.9, I'm going to get 145.8. So we're not going to forget 0.2 of a word, but just roll with it. For this, you could, however, if this was a word problem and it said, how many words do you know at week 3, you could say you still remember 145. You could round it up to 146, but somewhere in that ballpark. All right, then if I do 145.8 times 0.9, that's going to give me 131.22. And then the last one would be 118.098. So if we keep going with that multiplying by 0.9, it says if summer break is 16 weeks long, how many words will you know when you start back to school? So 16 weeks long would be a 4-month summer. Not going to be that long, God willing, although the way things are going right now, we'll see. So, but either way, if we kept multiplying by 0.9 till we got to 16 times, we'd end up with 37.06 words. So in all actuality, you know the phrase, hopefully you've heard the phrase, if you don't use it, you'll lose it. Language is something like that. If you don't practice those vocabulary words, if you don't refresh them, you're going to forget it. And the same with math. If you don't practice those skills, when you come back to it next year, you may be like, oh, well, I remember Miss George talked about that, but I don't remember actually how to do it. All right, so let's jump into doing formulas, because that's much easier than multiplying by 0.9 16 times. So the formulas are really straightforward. The first part is exactly the same as it was for exponential growth. Y equals a times b to the x, or times y equals a times b to the t. Either way works. So, and it's the same thing. Your a is your starting amount. B is, in this case, your decay factor instead of your growth factor. And t is still time. When we're doing exponential decay as a percent, like we did in that first problem, this is the formula we want to use. So this is almost identical to the exponential growth. The only thing that's different is that sign right there. Exponential decay is minus, exponential growth is plus. A is still your starting amount. T is still time. And R is still your rate. And you still have to turn your rate from a percent into a decimal before you plug it into the formula. But otherwise, it's exactly the same. And a lot of what you're going to see today mirrors what we talked about last week when we talked about exponential growth. It's pretty straightforward and pretty similar. The nice thing is it's a little shorter because we don't have the interest to talk about. So we talked about compounding interest and then continuously compounding interest. That's not a case. That's not an issue for exponential decay, so we won't have those extra formulas to juggle. All right, so this is an example of an exponential decay graph. The one time where exponential decay sometimes has a formula is it can come up in chemistry. For those of you all with Mr. George, I did check this isn't something you're going to get to this year. But if you are going down the road, and you may have heard of this before, half-life is just how long it takes something to decay, half of something to decay away. So if I had 100 grams of something, the half-life is how much time it would take for it to be just 50 grams left. And in this case, this is the half-life of antimony 125. I picked it because it's one of the shorter half-lives. It's only 2 years. So if you come over and look at the graph, that example is what I was talking about. We've got 100 to start with, and in 2 years, we're at 50. So in another 2 years, we should be at 25. And if we look, that's about right. All right, in another 2 years, half of 25 would be 12.5, and we're there. In another 2 years, half of 12.5 would be 6.25, and we're there, and so on. So that's what half-life is how long it takes for it to completely cut in half the amount that you have. And incidentally, this is what decay graphs look like. They're just almost the mirror images of exponential growth, because when we had exponential growth last week, they look like that. So it's just the mirror image of it. All right, so let's actually do some math with this. Okay, so this is the most common example that you'll see with exponential growth. It's talking about cars depreciating in value. Cars don't keep their same value. You drive them off the lot and they immediately drop in value, and the longer you have it, the less it's worth. So in this case, a new car depreciates, or purchased for $20,000, depreciates at the rate of 15% per year. All right, so we're going to write a function to model the value of the car as a function of the age of the car. Identify x and y. All right, so x is going to be age of the car in years. And then y is going to be the value of the car. And that'll be in dollars. All right, so starting amount, that's what goes in first. And we're dealing with a percent, so we're using this model for our formula, except they want us to use x instead of t. All right, so we're going to have y equals our starting amount, which is 20,000. And then 1 minus r, So our rate is 15% as a decimal. That's going to be 0.15. And then x is our exponent, so that's our model. We want to find the value of the car after 5 years. So we're going to take that model and we're going to put 5 in there as our exponent. Alright, so I'm going to jump over to Desmos to help us solve that. Before I do, just to make our lives a little easier, you can do the subtraction, just so you have less to type. So if you do 1 minus 0.15, you're going to get 0.85. Both versions here are fine. I don't have a preference. You can do whichever one you want. They both mean the exact same thing. Sometimes with this one, it's easier to see it if you've got your, if you're looking for what the rate is from the equation. For this one, it's really easy to think, okay, if I'm losing 15%, if I look at this one, okay, that means I have 85% left. So it just kind of depends on how you want to look at it and what's easier for you typing it in the calculator. Alright, so jumping over to Desmos, and type in our equation. It's y equals 20,000, and then times 0.85 to, and I'm going to use x for right now so I can turn this into a table. Alright, so let me zoom out just a bit. There we go. If you're doing this on a tablet, the pinch and zoom works really well. Actually, I'm going to adjust this a little bit. So a couple quick things. You can make your Desmos a little darker by turning on projector mode. And then I'm looking at my scale down here. This would mean this would be the price of the car after 200 years. Nobody is keeping a car for 200 years. I think the biggest one you might end up would be 20 years. So that's what I'm going to make my x-axis. Make it 0 to 20. And then we said that the car starts out being worth 20,000. So I'm going to make my y-axis go from 0 to 20,000. There we go. And now we can see the whole thing. Alright, so there's our graph. Alright, it's asking for how much it's worth after 5 years. Yep. So we can, oops, jumped around there. You can tap it here and trace. That works. You can get to 5. It's a little finicky trying to make that happen. So the other thing you can do is come over here and click this little gear. And when you click that, then you click the picture of the table. And it's going to take that equation and turn it into a table for you. And then you can type in whatever you want to look for. So in this case, I want to look for 5. And then it's just going to spit the value out at me. So after 5 years, that car is worth $88,074. Alright, if you've done that and you decide you don't want to see that anymore, you just go back to that gear and you hit the back arrow and it'll take you back to your equation. So you can see that either way. So however you want to do it works. Both of those are good. Okay, so going back to my table, type it in. I want to find out what the value is at 5. And that's where I get the 88,074. I'm sorry, not 88,000, 8,800. So 8,874.11. So that's how much the car will be worth after 5 years. So in just 5 years, the car goes from being worth $20,000 to $8,874,000. It's a big jump. That's why you'll hear a lot of people say they never will buy a new car, because they don't want to spend that money, drive it off the lot, and immediately waive a lot of that their investment, because the car is immediately worth less money. Alright, so now the flip side of that is questions asking, after how many years will the car's value be $3,000? Alright, so we can cheat a little bit on that one and have Desmos help us out. So we want to figure out when the Y is $3,000. So type that in, and we're going to have an equation. graph there, that horizontal line. We want to see where they intersect. That one's a little funkier, so I'm going to pinch and zoom just a bit so we can see a little more accurately. And so it's about 11.6 years. That's as detailed as we need to get. So 11.6 years. All right, so it's basically the same premise as what we did before with exponential growth in going through and typing in our equation, looking at the table to find our y values. And when we have a y value and we're looking for the x value, then we type in the equation and we use the graph to find the intersection point. We'll get into later this semester how to actually solve that equation so you don't have to use the intersection point, but that's a little bit down the road. All right, so now we've talked about exponential growth and exponential decay. How can you tell the difference? Well, one obviously is the graph. So if it looks like this, that's exponential growth. If it looks like this, it's exponential decay. Pretty straightforward. The other way you can tell is you want to look at the formula. And in particular, what you're looking for is the number inside the parentheses, the b. So if b is greater than 1, that's exponential growth. So I'm talking about this number right here, the part inside the parentheses. So if that is bigger than 1, you're dealing with exponential growth. If b is in between 0 and 1, if it's a decimal smaller than 1, so 0.5, 0.7, 0.2, 0.3 repeating, whatever, as long as it's a decimal smaller than 1, that's exponential decay. I just realized I didn't label these. So this one's growth and decay. If you stop and think about it, it makes sense. If you follow your graph, it's getting bigger, therefore it's growth. And follow this graph, it's getting smaller, therefore it's decay. Same over here. If you're multiplying by a number bigger than 1, that means it's going to get bigger, so that's exponential growth. If you're multiplying by a number smaller than 1 by a decimal, it's going to make your answer smaller, and so that would be exponential decay. All right, so all I'm going to do with these is just look at the middle number. That's all I care about. Ignore everything else right now. All right, so for that first one, 2's inside the parentheses, 2's bigger than 1, so that's exponential growth. All right, for that middle one in the top row, it's 0.6. 0.6 is smaller than 1, so that's exponential decay. For this one, it's 1.5. That's bigger than 1, so it's exponential growth. This is 1 plus 0.25, so that would be 1.25 inside, so that has to be growth. For this one, it's 1 minus 0.7, so that would end up being 0.3 inside the parentheses, so that's decay. And then over here, it's 0.8 inside the parentheses. It's also decay. If you notice, I didn't say anything about the signs. Don't care. For exponential growth and decay, when we're dealing with our basic formulas, all we're worried about is your b value, your growth or decay factor. If it's bigger than 1, then it's growth. If it's in between 0 and 1, it's decay. Now the last thing to look at that goes along with exponential decay is the decay with that natural base e. So we talked about growth with base e, and we used it in our continuously compounding interest. That was the shampoo formula. But for this one, this is where it changes. For it to be exponential decay with natural base e, it is going to have a negative exponent. This is what the graph looks like. E is still our 2.718, still the same as it was. And where you're going to see this is a lot of times in this example, when we're dealing with business and we're saying that we've got some kind of formula that helps us predict how many things that are going to sell. Just like with a quadratic regression, we had that as well. It can pop up as well for this. So for example 4, we've got annual sales of a certain product, can be modeled by the function s equals 60,000 times e to the negative 0.15 t power. It's kind of a mouthful. S is the number of units sold, and t is the number of years since the product went on the market. All right, so we're going to graph it, and then we're going to use the graph to estimate the annual sales 6 years after the product went on the market. All right, so I'm going to minimize that for a second. Actually, I'm just going to get rid of it. All right, so I'm going to clear out what we did over here at Desmos, and then I'm going to click the little house button so it goes back to normal. All right, so we got y equals 60,000. And I got to go in to pull up e, and then exponent. And then depending on how you feel about this, you can put parentheses around your exponent. And if you're using a TI-83 or 84, I would, just because the operating system gets funky sometimes with its order of operations. If you're doing Desmos or you have a newer operating system on those TIs, as long as you can tell that it's all raised, that it's all an exponent, you're good. You don't need the parentheses. So we've got negative 0.15. We'll use x instead of t. Okay, so that's our equation. If I look at the graph, I can't see anything. All right, so we know we're starting with 60,000, and then it's decreasing. All right, so let's take a look at this. We're also talking about years since a product went on the market. All right, so let's try 0 to 20. That worked well for us last time. So we're going to look at how long something's on the market for 20 years. And then we know it has to go all the way up to 60,000. Oh. All right, so here's our curve. And it's asking us, what is it 6 years after the product went on the market? Oops. So here's 6 years. I would be looking for right here. And I can get close. But it's also kind of hard and a little finicky in there to get it to get just right. So you can come over here and use their table like we did before. And then just tell it you want to see what it will be after 6. And so there we go. So after 6, we're going to have that product line is going to be selling 24,394 units. So real quick, that had a 0.18, but I didn't include it. Because if we're selling things, odds are we're not able to sell like 0.18 of a product. If it's a Twinkie, you can't sell 20% of a Twinkie. Nobody's going to buy it. They either want the entire Twinkie or none at all. So in this case, we got to round down to the 394 units. All right, so that is it on notes for today. I do want to point out one quick thing, if you'll bear with me while I log into Canvas. Actually, no, I'm going to pause you for a second while I log into Canvas. Okay, I'm back. All right, so jumping into Canvas, first off, if you need it, make sure you go forth and look at the motivational baby chick on the front if you need it. I sometimes do this week. All right, so I wanted to draw your attention to a couple of things. I am still dealing with your textbook publisher, but it looks like we're almost there. So I am going to have textbook numbers to give you guys in a little bit. Hopefully tomorrow. They've been going back and forth between 2 different customer service people trying to make this happen. So when I get that, I will post it in this distance learning resources and make sure you've got that. I had a request on the Google form today. Somebody said that they were really having a hard time trying to get themselves motivated to do their work while they're home, that it was really hard and they didn't know where to start and it was just really overwhelming. So in here, I went through and listed some strategies that I use. There's like 5 or 6 things in here. Take a second if you're struggling with that and read over it and see if any one or two of those sound like it might be something you want to try. So just as a heads up, that's there. We're going to stick with the same office hours this week, so that'll be Thursday at 3. If that doesn't work for you, email me and we will set up a different time. There were a couple of you in the Google form that I got today that said that time was bad for you, so get with me and we'll figure out a different time. I'm happy to do 2, so that shouldn't be an issue. Also, I put in a stress relief module. I'm going to keep adding stuff, so if you find ridiculous memes and things like that, please send them to me and I will add it to the list. And then again, remember all of your things are right here for this unit. I'm going to keep adding. So we've got 1.3, which is what we're talking about right now, and then 1.4 is exponential regression. They'll go in here. Try to get these done by April 3rd. That will keep you on pace. That being said, if your life does not allow that to happen, that is fine. Just communicate with me, okay? Don't just disappear. Send me an email, say, hey, Miss G, this is what's going on. I'm going to get you this stuff by the weekend, by Monday, whatever. That's fine. Just talk to me, okay? All right, my loves. I hope you're hanging in there and you're doing okay. I miss you guys. If you need anything at all, I mean it, send me an email, all right? I will see you guys, I will talk to you guys later and hopefully see you on Thursday in the office hours. Be good, be safe.